Hello, and this presentation is meant to be an introduction to basic logic gates for electricians. And what that means is we'll be looking at relay ladder logic and the explanation of the logic gates and the truth tables associated with them. So let's get started. In this video, we'll look at the first 5 gates. The first one we'll look at is the AND gate. From there, we'll take a look at the OR gate, as well as we'll look at the truth tables for each gate as we progress. Next, we'll look at the NOT gate or the inverter, and then we'll see how we can use the inverter to turn the AND gate into a NAND gate, and use the inverter to turn the OR gate into a NOR gate. And through all this, we'll also use ladder logic or relay logic to explain the functionality of each of these gates. Our first gate we're going to look at is the AND gate. Now the input side, which is on the left-hand side, you'll see A and B. So I have inputs A and B. And that side is flat. And on the output side, which is rounded, I have output Y. This is the ladder logic for an AND gate. And if you're familiar with ladder logic, you'll clearly see that I have to press buttons both A and B to energize coil M, which will close contacts M and light the pilot light Y, or the yellow pilot light. Truth tables are a way for us to keep track of the digital logic associated with gates. So here you can see I have 3 columns. Column 1 is input A, and column 2 is input B, and then my third column is my output column. Now with truth tables, there's a couple of terms that we use with those. A 0 is what we considered an off state, or a false statement, or a no. A 1 is considered a yes, or a true statement, or an on. Much like digital, zeros are off and ones are on. So, if we carry on with this, right now I am not pressing button A, nor am I pressing button B. So, coil M is not energized. Therefore, contact M is not pulled in, and my light is not on. So A is false, B is false, therefore Y is false. If I should press button B, I still don't have a complete line on line 1. So current can't get through and magnetize my coil and pull in my contacts. Therefore, if A is false and B is true, output Y is still false. If I should just push button A, it's the exact same thing. A is true, but B is false. So my output Y is also false or off. But just as in its name says, the AND gate, when I press A and B, I energize coil M, which closes M contacts, which turns on my yellow pilot light. So A and B equal output Y. The next gate we'll look at is the OR gate. Now each symbol is slightly different from the other, so we can differentiate them one from another. So here on the output side, it's pointed. So it's kind of pointing towards the Y. The input side, where A and B is located, is slightly curved. So again, it's slightly different than the AND gate. Allow us to tell the difference between the two. This is the relay logic for a simple OR gate. And again, if you're familiar with ladder logic, you can see that if I press button A or I press button B, then I can energize coil M, closing contact M, turning on my yellow pilot light. OR functions are typically wired in parallel, whereas in the previous example, AND functions are usually wired in series. Again, we'll take a look at the truth table for the OR gate. So if I do not press A and I do not press B, so A or B is false, then output Y is false. If I should press button B, then I do have a path on the second line that will energize coil M, which will pull in M contacts and turn on my yellow pilot light. So if I have B, I also have Y. If I should press A, well, again, line 1 will become true, energizing M coil, closing M contacts, and turning on my yellow pilot light. If I should press A or B or both, then I can get current to my coil, closing my contacts, and turning on my yellow pilot light. In the previous examples, when we used relay logic, we were using normally open contacts being controlled by coil M, so that when coil M energized, it closed the contacts. But what happens if I want to use normally closed contacts? Well, that's where the inverter gate, or the NOT gate, comes into play. Here's the relay logic of using a normally closed contact. And as you can see, when you don't press button A, M coil is not energized, but my yellow pilot light is wired up with a normally closed contact, so it already has power. So the yellow light is on even though I'm not pressing the A button. In this simple example with the inverter, there's only one input and one output. So my truth table is simplified to show that. So now, when I don't press button A, I have an output or a true output on Y. So A naught equals Y. But when I press button A, I don't have Y. So A equals Y naught. It's an inverter. It's just the opposite function. When I press A, I turn the light off. When I don't press A, the light is on. It acts just like a normally closed set of contacts. Let's now take our NOT gate, or an inverter, and we'll add it to one of our other gates. And we'll start off with the AND gate. So what happens when we take the AND gate and we add an inverter to the output? Well, we get a knotted AND gate. We call that the NAND gate. And the symbol for the NAND gate is, well, basically an AND gate, A and B. And again, it's flat on one side and curved on the other. Instead of drawing the whole inverter, we just take the inversion bubble and add it to the end of the AND gate so that we know that the output has been inverted. We call it an inverter bubble. So now we have A and B naught will equal Y. So let's take a look at the relay logic and the truth table associated with this particular gate. So here we have our NAND gate. And again, it's an AND gate, A and B on the input, a rounded output, and an inversion bubble on the output so that we know that it's a knotted AND gate. The relay logic is very similar to the AND gate, but what we've done is we've traded out the normally open contacts on the second line feeding the light to a normally closed set of contacts. So now the light is always on. So when I don't press A and I don't press B, my coil is not energized. Therefore, my M contacts stay closed and my light remains on. If I should just press input B, well, I still don't have a complete line. Therefore, my coil is not energized, my contacts remain closed, and my light remains on. If I should just press button A or input A, my coil is still not energized on line 1. Therefore, my contacts remain closed and my light is still on. It's only when I press A and B do I not have an output on Y. And that's my NAND function. A and B will equal Y naught, or Y is false. Now let's do the same thing with the OR gate. So let's take a simple OR gate, rounded on the input, pointy on the output, and we'll add an inverter to the output of the OR gate. So now I've got a knotted or an inverted OR gate. And again, just like the NAND gate, instead of drawing the whole inverter, all we'll do is we'll just take the inversion bubble off the inverter and leave it on the end of the OR gate so that we know that the output of the OR gate has been knotted and that we have a knotted OR gate or a NOR gate. So again, we have our knotted OR gate or our NOR gate symbol. And here's our relay logic for our NOR gate. And similar to our OR gate, OR functions are wired in parallel, except for this time we used a normally closed contact on the output instead of a normally open contact on the output. So even when I'm not pressing A or pressing B, the light is on. So let's look at the truth table. When I don't press A or don't press B, then my light is on. But if I should press B, I do have a path to energize coil M, which opens contacts M on the third line, turning my light off. Same as if I should press button A by itself. Line 1 becomes true, energizing my coil, opening up my M contacts on line 3, turning my light off. If I should press A or B, I do not have my light on. So, A or B will not result in my light being on. So there you have it. Those are our first 5 gates. We've got the AND gate, where A and B will result in the light coming on. You've got your OR gate, where A or B will result in the output being true or on. Then we introduced the NOT gate, or the inverter, which acts like a set of normally closed contacts. And when attached to the output of the AND or the OR gate, then we end up with the NAND as well as the NOR gate, where I need both A and B to turn off the output in Y. And for the second one, for the NOR gate, A or B will result in turning off my output Y. I hope this helped, and I look forward to seeing you in future videos. Thanks for watching.